with that, and view, full screen, and away we go. Let's see if I can get that square a little bit right there. Okay, what are we studying? Chemistry. See if I can get a pen that will work. Some of these are about shot. By definition, it focuses on the study of matter. Now, the definition I use is verbaceous, and so it's kind of a long thing, but it embodies all of that structure that we're going to use. Chemistry is the study of the structure, composition, and properties of matter. And the changes in composition, structure, and properties that matter undergo. Okay, like I say, it's somewhat wordy, but it does embody three very important issues that you need to keep in your mind throughout the entire course. This is not an inorganic course. Some people think it is. It's not. It's a survey course. It embodies a lot of individual topics, and in that context, what I tell people, it's like a toolbox. We're building our toolbox of chemistry subjects and putting them in that toolbox throughout the course of the year. By embodying yourself or understanding these subjects as we go through, you build the ability to go on to the next level, a specialty course, which is, of course, something like organic chemistry or analytical chemistry, biochemistry, and so forth like that. So the nature of what you're studying, and the point of my comment, is that take these as individual learning experiences as little tools. Now, I didn't say forget the one you learned yesterday and concentrate on one. They all tie one into the other systematically. But this is what this course is. Now, here, the structure, composition, and properties will embody the most important elements of studying chemistry. Most people that study chemistry, for whatever reason, will revolve around one of three or all of these subjects. The composition, of course, is what is it made out of? Structure, how does it go together? And what does it do? And how, if we change it or interact it with our environment, what will it do in terms of changes? Now, matter is the core issue. And it's anything having mass or weight in, if you're in a given reference frame, having mass and occupies space. So that gives us a very broad collection of items, and you as a student of chemistry will find that a daunting task to try to study it in that context. So what my job is to systematically structure this course so that it's easier to digest, and that as you go through you build it systematically. Now, matter in itself is really divided into two major concepts. Mixtures and substances. Now that's the big picture issue of matter, and that everything around you kind of boils down to those two major words. Now, if we get into mixtures, which will be more in the area of solutions and combinations of substances, we're talking about homogeneous and heterogeneous mixtures, and that format. A heterogeneous mixture is simply characterized as a combination of substances with inconsistent properties throughout. You can find all this in a textbook or look it up on internet or wherever. I'm not going to try to write out all the definitions for you, but heterogeneous is inconsistent properties. Gunpowder and sulfur. Gunpowder is a very, very dark black color, and sulfur is a bright yellow color. And you can see the different components if you mix them together. If you tested it and evaluated the percent composition, you'd find that different samples in different locations would be different. They would not all conform to the same value. However, on the other side of this coin, we have homogeneous solutions or homogeneous mixtures, which are solutions. And so we look at consistent properties throughout. Throughout a mixture. A salt water sample would, if you took samples from different parts of a salt water solution, you would find the percent composition would always be the same. Now what I've done is I've tried to break this down from a indigestible mass of material down to something that's a little more digestible in what we're trying to talk about. And so I will continue in that context. Substances are both homogeneous, and there are two substances classifications. Atoms or elements, let's just put elements down. And compounds. Both are homogeneous. Now, we're familiar with elements from previous courses in terms of definitions. It's the smallest entity of a substance, okay, that has specific chemical and physical properties. Now I'll make a smallest entity, give you buzzwords, entity of a substance that has specific chemical and physical properties. Here's the key. It cannot be broken down by ordinary physical or chemical means. What do I mean by heat, light, electricity? Will not break down the elements. You have to do something very unique to them. On the other hand, if you have compounds, they are the smallest, it's the same definition, except they are the smallest entity of a substance that can be broken down by ordinary physical or chemical means, heat, light, and electricity. Compounds are two or more elements in the context of its classifications. So we're beginning to break the concept of matter down to something that is in smaller boxes, and your job is to study the material and information that's in a given box. Well, in the course that you're taking, it is a systematic study based upon Dalton's atomic theory. So the Gen Chem course is based upon the postulates of John Dalton's atomic theory. We will study that in more detail as we get deeper into the course in terms of the kinetic molecular theories and stuff of that nature. But right now, Dalton's postulated, and all of what he came up with was based upon the scientific method. So, you know, there's a realism issue that associates with this. Well, he proposed that all matter, first of all, is composed of small particles. And they're the ultimate particles in his time, called atoms. But we know today that the atom can be broken down to even smaller components. So I'm going to modify Dalton's postulate collection by, instead of putting in atoms first, I'm going to precede that with fundamental particles, protons, neutrons, electrons, and then build from there. The course you're taking will do just that. When we get more into chapter 2, it will start by talking about fundamental particles. Those are protons, neutrons, and electrons, the three fundamental particles that make up the atom. How they go together we will study at the appropriate time and learn how to use the periodic table to figure out how many neutrons, protons, and electrons are associated with a given element. And of course, putting these together properly leads us to atoms. Atoms are these, again, a single atom is in itself a nucleus and a collection of electrons, okay? But when we start talking about elements, we multiply that into a large number of atoms. So when we talk about atoms, we're talking about individual components or single entities. When we're talking about elements, we're still talking about atoms, but we're talking about a whole lot of them. So it's a matter of semantics, really, as we go through this. So atoms will lead us to the study of elements. We've already defined those in the context of classifying matter a little earlier. Now, as we look at elements, they are the most fundamental atoms, then we build the elements, and so the logical step after that would be to look at the periodic table and how to use it, how it's structured. A little bit of history. I'm not going to beat you to death with Mendeleev and H.J. Moseley's postulates and stuff, but the structure of the periodic table is very unique, and it goes together in a certain format, so you can use it to predict behavior and characteristics of elements. All right, next thing, once we understand everything there is to know about elements, we put the elements together, and those form molecules. So the chapter, or in the same chapter, but it's the latter part of that same chapter, it talks about molecules and molecular structure and how it comes together, and we talk about the formulas and so forth. And in the same way that we kind of relate atoms and elements, we do molecules and compounds. So molecule would be considered an individual entity of the substance, like H2O or NaCl or something like that. But when we take a lot of molecules, we're talking about compounds. So they're really the same, but it's a matter of semantics again. If you're talking about a molecule, an individual entity, compounds, a whole lot of those individual entities. Okay, well, we have elements and atoms and molecules and compounds. Now what do we do with them? We interact those through a process known as chemical reactions. So after you are experts in those subjects, we will talk about the organization, classification, and use of chemical reactions. I abbreviate reactions incessantly with RXN, so Some people will write it down. That's a prescription. That's what a pharmacist would write me, RXN. Anyway, reactions, of course, we recognize and have experience with those in terms of their two-dimensional structure, reactants and products, and a whole bunch of confusion that goes with them and balancing. And then we'll do a lot of that and review a lot of that as we go through the course. Now, in any chemical reaction, there are only three things that can be produced. That's kind of maybe took some people back. But if you think about it, it's solids, liquids, and gases. That's it. Now, there is a fourth dimension of material called the plasmas, and those exist above 5,000 degrees where the entire material is ripped apart and there is no entity called an atom or a molecule. That's outside the scope of the course. Our world is in the box that contains molecules, atoms, in their collective state, if you will. So, chemical reactions will produce states of matter. Solids, liquids, and gases. So, of course, there's zillions of solids and liquids and gases and the conditions under which they exist you have to study and learn how they are produced and so forth like that. But a solid is in itself homogeneous, the substance. The liquid is a substance if it's a compound, or a gas is a substance. They're homogeneous in their nature. They only depart from that when they're mixed together. And mixing solids, liquids, and gases produces solutions. Solutions, we go back to the classification of matter, the homogeneous side of mixtures. Okay? Solutions, by definition, are homogeneous mixtures. Consistent properties throughout. Okay? The air that we're breathing in this room is a mixture, a homogeneous mixture, and it's a solution of whatever components that exist within the air. What you're looking at here on the screen is the organization of your study of General Chemistry 1. This is how it came together. When Dalton postulated the atomic theory, he did not know about the fundamental particles. And so he really started right here. But all of the other components of this came from his atomic theory. I would encourage you, for a historical point of view, if you like that kind of stuff, go online, look up some YouTubes on Dalton's atomic theory. His unique representation of elements is very interesting. He would represent, say, oxygen like that, or hydrogen, or nitrogen, or some other elements that he's working with, and so forth. So it was very interesting, and it's watching some of the historical development of what he thought the symbology would be for the various elements and things. But we know today, and we will use the periodic chart for sure. I won't ask you, well, what's the black dot mean? Okay, so we have now a perception of Chem 1. Now, just for a sidebar, I'm going to tell you what Chem 2 is. It is a natural evolution from this in terms of a specific study of reactions. So many of you will be moving on to Chem 2, which is part of your curriculum, and you can expect a major portion of that subject to be revolve around, well, how do we study chemical reactions? I'm going to give you the generic, and then we'll be back into the basics again. But when you study chemical reactions, there are three big picture topics that we look at in terms of studying them. There's chemical kinetics, I'll list them here. This deals with the speed of a reaction, how fast it proceeds from out of the starting gate, so to speak, and how long it takes to reach an equilibrium condition. Chemical equilibrium would then be the next top major picture topic. Which is called the extent of reaction. When A and B come together in large quantities, A finds B very quickly in the beginning of the reaction, but as the reaction is saturated with compound from AB, A doesn't find B very easily, and so the reaction slows down and it ultimately reaches a constant concentration. And when the constant concentration occurs, that's where we start the study of equilibrium concepts. And you're not responsible for repeating that, obviously, until you get to Chem 2. But I just want to show you how it evolves past the concepts we'll be studying. And the last major big picture topic that's used to study chemical reactions is chemical thermodynamics. Chemical thermodynamics, in its basic definition, is important, and I don't want to minimize it, but its purpose is even more important. The purpose of thermodynamics is to define the feasibility of a chemical process, or a physical process in some cases. Will it work? Will it not work when you pour A and B together? Well, thermodynamics has mathematical methods, and you plug in the formulas, and yeah, it works. No, it don't work. And you will learn those at the appropriate time when you get to thermodynamics. Thermodynamics is a very young science. When we talk about the study of sciences and chemical reactions, kinetics and equilibrium are very old sciences. Thermodynamics evolved from the need to study steam engines back in the Industrial Revolution, and so it began to evolve from there. It's a very sophisticated science, and is very beautiful science in terms of treating physical and chemical nature of our world. But anyway, it is a very, very young science. So I wanted to kind of show you where you go from out of Chem 1 into Chem 2. Now, at this point, once you pass this subject, the thermodynamics, you enter into a world of specialty topics. You have your toolbox full of now general chemistry tools. You are now able to go on to these specific topics that will use those tools. Organic chemistry, analytical chemistry, biochemistry, polymer chemistry, industrial formulation chemistry, and on and on and on. Those are specific entities that draw on constantly on the material you're about to learn. So we want you to keep in mind, as far as the perspective of what we're doing, is building a toolbox that you can use for study of very specific topics. Somebody in here may be going into medicinal chemistry. Well, it will not use every tool in the toolbox, but you will certainly need to be expert, so to speak, in the ones you do use. And we will cover as many of those as we can. Okay. The next topic is the scientific method. This is something that you have been exposed to over and over and over from the first science course to now. The points or postulates, if you will, of the scientific method are unchanging. And I'm not going to try to change them. But I am going to try to instill in you a different perspective that you may not have heard of. Many of the students that I get originally, new students, have an understanding of what the scientific method is. It's a systematic way of studying a topic, a subject. Well, that's fine. But there's something even deeper than that in terms of your relationship to whatever you're studying. And that is very important that you understand that as you go forward in your work in sciences. So we'll start simply by listing the postulates very quickly, and these are I'd say 90% of you already know. Identify the problem. Okay, we're going to study stars. Who knows? The ocean water. Certain flowers. Doesn't matter. You identify what you're going to study. Then you collect information. On the subject you are interested in. Okay? The subject of interest is what I usually call it. Okay? The object of interest, subject of interest. As you collect information, you know, we're talking about studying about flowers or ocean water or whatever, fish, you come up with an idea that hasn't been touched on. You want to learn more about it. And you establish what we call a question in your mind, which is the problem. Okay. So as you read along in part 2 of this effort, what happens? You get an idea of how to solve the question. Oh yeah, the same way math. You start studying a topic in math, you reading along, oh, I can solve that problem now. And you scratch along and apply what you think. That's called an hypothesis. You form hypothesis, which is simply put an educated guess of how to solve the problem. It may be right, it may be wrong, but it's based upon logical concepts that you've been reading about. It's an expectation. If I do this, I should get this. If I do that, I should get this. Expectations in chemistry. Now, it's a big word also. So, you apply your hypothesis. To prove your hypothesis, you set up an experimental. Okay? So, you prove hypothesis through experimental methods. And you design your experiment based upon what you've studied and read. Now, some of the things that you study and are interested in reading, there's been tons and tons of work already done, so you get a paper and kind of model your work right after that. And so the experiment evolves very naturally from the works. But if you are trying to put a man on the moon and you're living in 1955, you've got to create everything on the way to the moon. As you go through your experimental and you started getting the results, these results are either right and support your hypothesis or wrong, and they don't support your hypothesis, or you form conclusions. They can be right, support hypothesis. So that's the object of science, is to be able to support whatever you claim. You don't just make some off-the-wall statement about, well, all flowers fly. Okay? Well, that's not true. Maybe some seeds of the flowers fly, but not all of them fly. But you go out and you start throwing flowers, they all kind of, and most of them don't. So you support your hypothesis. or it does not. You're wrong.
The screen went off.
You don't commit hara-kiri. You screensaver. I don't think we're saving anything, to tell you the truth. Okay. Experiments. Say you run a mass number of experiments and they do not support your hypothesis, and you scratch your head. What do? Simple. You go back to collecting more information and repeat. So you go back and say, I worked out this math problem. Doesn't match the answer in the back of the book. What do you naturally do? You go back and look at the theory again, and you read it all, and then when the epiphany shows up eventually. Sometimes science doesn't have an answer. Okay? We haven't found anti-gravity machines yet. There's some weird stuff on YouTube, but I don't think it is the truth. I don't think anybody could prove it. But at any rate, okay, this is something that I think everybody is comfortable with in terms of how to solve a problem in the scientific approach. Now, what I want you to understand is what your position is relative to studying an object of interest. In the world of scientific endeavors, we divide our work, or the content of our work, into two entities: a system and surroundings. So what I want you to do is make a T-table right here. This is a simple concept, nothing very complex. And on the left, I want you to put the system and surroundings, like that. The system is the object of interest, or subject of interest. This is what you are interested in studying. Acid-base reaction or whatever. Surroundings is simply everything else. In science, the principal function of experimentation is to make measurements. Yes? I think we all appreciate that. We got to do data ruler. I used to have a ruler up here. We got a project, and so a problem, and so we measure using the tool like that. Well, what does this mean? What does the tool mean? Well, tools go on that side. They receive information, okay, from the object of interest. Now, one of the things that I want you to understand here, and this is why I present this, you never, ever measure, interpret or come to any conclusions from the object of interest. It's the information that the object sends to you or explains to you. You have to learn its language. So this tools are devices that receive signals from system or object of interest. You never, ever measure anything from the object of interest within the object of interest itself. What you are doing is using a device that will receive information from that object of interest and interpreting how that object is affecting the surroundings. So there's always information proceeding toward whatever device you have, and it's a part of the surroundings. Now you as a student, me as a student of sciences, are part of these devices. We're in the collection of devices that receive information. We're observers. And here's the key. Without your presence, there's no science. The objects of interest don't mean anything. So the fact that you are present in the experimental environment provides the conduit through which objects of interest send information. So that information comes through you. So what do we do with the information? We interpret it and draw conclusions about what the object of interest is. Take the wall. What color is it? Well, some people would say blue in general. Okay? How do you know? That wall is sending you signals relative to its color. Okay? And you could go even deeper than that. Well, how do I receive those signals? Of course, the optics in the eye, and on and on and on. Like that. You are a receiver and part of surroundings. And as you go through the scientific method, you need to keep that in mind, that you are always just receiving information. Einstein made the statement that in order to understand the universe, you must first learn the language of the universe. If I can get my pens to start work for me. Go out buy a bunch. Oh, that's a terrible warning. Try that again. Hot and cold. How do you know? Maybe you have a liquid somewhere and you want to know whether it's hot or cold. Well, it's certainly relative to you as an observer. From a basic standpoint, 100,000 years ago, man did not have thermometers. So how would he have determined if something is hot or cold? Put his finger in it or whatever. That's a receiver device. What happens at the moment he plunges his finger into that liquid or whatever, fire or whatever? He's got a signal being sent to the issue, to him as a receiver. He then interprets the outcome, what that stuff is. You don't go out and stick your finger in a campfire, and the coals in the campfire. Experience tells you this. Maybe somebody told you not to and you just took their word for it. Don't go out there to prove anything. But if you had to prove it, you are a device to receive information. And that's the whole essence of science. You design devices. That's the whole concept. That will receive signals from the objects of interest. And when those signals come to you, you write them down or they come to you in a certain format. And from that format, you draw a conclusion as to hot or cold, soft or hard, stretchy or resistant, whatever. As you make those interpretations, you create the universe that you live in. That's the philosophy of science. You create it. Without your presence, there is no object of interest. There is no language. There is no science. So while you are involved in this, keep that in mind, that you are the receiver of everything we do and talk about. You draw in this language and then you put it in a form that hopefully others can understand and will make sense and is logical. And you present it to the world that this is a campfire, it is hot, don't touch it. Okay, this is an iceberg, it is cold, don't stick your tongue on it. All right, so the issue is you test it and the signals are sent to you and you interpret those signals. Well, this whole course is about learning the language that is being sent to you by the various chemistry things. That's our focus. You go to physics class, you'll have physical things, physics stuff. Dropping balls, blowing up stuff. Well, that's a little chemistry too. But I wanted to emphasize the idea of where you are in the context of the world of science. Hopefully that will kind of carry, it's nothing you have to repeat every time you step in the door of a laboratory, but it's something that you need to understand. When you measure the change in temperature of something, you just put a thermometer and watch the temperature change. And so it's a device. When you see the temperature go up, it's getting hotter. You made an interpretation. It sent you some language and you made an interpretation. Then you write it down, hotter, whatever. Okay, so that brings us through the scientific method. Now we get into the essence of science, and we just talked about the object of interest and you as a receiver of the languages. And so how do we receive that language? By measurements. So we now look at science of measurement. Of course, many of these topics, again, will be very familiar to you, but I'm going to systematically build them so that you can use them. And hopefully, if you're not familiar with them, you will learn from my comments and hopefully become a good scientist. We begin with the importance of measurement, so I hope you can give me some important pens. This is something that when you go into the laboratory you're not going to repeat, but you need an appreciation for it, so I'm going to give you that. Big deal. It's easy to remember. M-A-L-T. It's an acronym I came across 100 years ago that tells me the the importance of measurement. It gives meaning to environment. When we say it gives meaning to our environment, we have to establish some fundamental quantities we'll talk about in a few minutes. Length, weight, time, lumens, and the such. Okay? Meaning to our environment. It answers questions. When you make a measurement because you had a question. How long, how high, how wide, how hot, how cold. So you use a device to acquire numbers that define what you're trying to study. It limits behavior. Once you understand what that object of interest is sending to you, you respond to it to a certain extent or limit. Campfire, you don't stick your hand in it, but you can get up close enough to get some warmth. So you have a limit of behavior. So it limits the behavior. if you drive 60 miles an hour through a school zone and our illustrious policeman sees you, he's going to limit your behavior real quick. So this is the idea of measurements. 60 miles an hour is not the speed you should be going through a school zone. Okay? And it's a tool for understanding, so that you can communicate. This tool for communicating, and you can put out there communication. I'll write too fast. So that you can construct some presentation that's an interpretation of the signals that were essentially sent to you. Now, when we measure something or study something, we have to fundamentally make sense. You don't want to be just a babbling idiot when you try to explain a campfire or how a rocket works. You have to have a logical approach to scientific presentation. And here is, that's what we call conditions for meaningful measurements. This establishes the abstract. When you are in the universe, you have to establish certain descriptive words that define what you're trying to measure. And that leads you to a description of what's around you. For example, the distance between the walls in this room, or the floor and the ceiling. You have to establish something that makes sense. So you define a thing called length, width, height, a distance factor. Or if you're trying to determine the force that an object is on applying to a table, as this book does, it would be another descriptive element, weight. And another element is, how long am I going to be babbling up here and boring you to death? Okay, well, that's time. So you have to establish this and use those terminologies to explain what you're studying. And so when we talk about a meaningful measurement, there are things that have to be presented, and you do this logically and automatically. But I'm just making you aware of what you do automatically. One, you define always what you're trying to study. Define the object of interest: length, weight, time, brightness, whatever. Now, once you define length, for example, there are a lot of lengths. So you have to establish a standard of length from which everything else is compared. So we standardize the dimension, defining fundamental quantity. I'll put that up here. And you standardize the quantity in terms of something everybody would understand. We understand the device I'm holding in my hand as a 1 foot ruler. Okay? 1 foot is the standard in the English system. And somewhere I had a meter stick. It's around here somewhere. And yeah, there it is over there. A lot of good it's doing me. It represents the standard of length in, of course, the metric system, as you know. And we'll use those. So we standardize, and we finally, when we make our measurement of whatever it is, we compare to that standard. Define, standardize, and compare. So anytime you make a communication in science, or generally anything, in order to make sense at all, somebody has to understand what you're talking about. You're talking about length, weight, time. And you will speak logically in terms of the standard that's been created. Well, this is 10 times the standard of length, or something of that nature. And if you establish the length as a meter stick, it's 10 meters, okay, decameter. And so you have to have a logical approach to presenting. Well, when you write up a document and you're trying to present the conclusions of a scientific study, you certainly want to keep these three elements in mind. What are you studying? Be sure you define what you're studying. We're going to, and I'll show you how to do that. If we're studying a density, what is density? So you define that. What is the standard density for a given object? What does everybody believe this density should be? And then you go make measurements, and you come out and you compare density of air to density of something else. So you define, you standardize, and you compare, and you write your presentation like that, and you present everything like that. Okay? So when you do a measurement, we will establish the context of the measurement and sciences from that point of view. Define, standardize, and compare. What have others done? Okay? So you establish a standard of what everybody else has done, and you do the experiment and you compare it to what they've done. And you tell people about that. That's the whole essence of communicating through measurements. Okay. Now we get a little more specific about what measurement ideas. What's the content of a measurement? Two parts, actually three, but we'll throw in that third part as scientific measurement. A number, a unit, and an uncertainty. There are scientific measurements and there are absolute measurements. What we're going to be working with, of course, is the idea of scientific measurements, which evolve in this context, number, unit, and uncertainty. But in absolute measurements, we're talking about 5 apples in a basket. There's not really a lot of uncertainty in that issue, okay? So when we talk about measurements and measurement concepts, we'll be working with the idea of scientific measurements, not absolute measurements that constitute the 5 apples in the basket kind of thing. Well, it might be part of that, but it will still be defined in terms of scientific context. Okay, what about numbers? What do we need to know about the idea of numbers? In terms of presenting scientific numbers, we define our results in terms of significant figures and error analysis. So if you have a measurement and you've made a number of measurements, is the average of the measurements plus or minus an uncertainty factor. The uncertainty in the number of how your measurements gives your work credibility. So the uncertainty factor, along with the average, provides a very important aspect of you as a scientist, credibility. I think we all appreciate by now that one data point is not going to define the outcome of an experiment. We've been taught that since day one. And you're going to want to just run it one time when you get to lab. All students do. They want to get in, get out, which is understandable. Okay, you don't want to die in a lab. But if you're going to make a presentation on your object of interest, you want that presentation to be credible. You want to be infallible. You want to be perfect in terms of what you're presenting about your object of interest. And to do that, you have to be able to apply uncertainty factors to the work that you've done. And this comes out in the context of significant figures in one issue and in precision accuracy. And we'll work with the precision accuracy later in the class, and it's part of our lab today. Significant figures. You make a measurement using some devices, a top loader balance, a ruler, or whatever, spectrophotometer, gas chromatograph, any number of devices the world's invented. You get a series of numbers, okay? The significant numbers in a measurement are all digits known with absolute certainty, plus one uncertain digit. Plus one digit. When you measure a line, here, let me put it right about there, I guess, the length. I'll look at it as 4, a little more than an eighth, almost 3/16. Well, you may look at it and say it's 1/8 only, and somebody else may, I don't stop at 4. Yeah. Needs his eyes checked or what. But the idea is measurements vary in terms of how they are presented. So how do you deal with that in terms of measurements? They're significant figures. There are rules for significant figures. Now I'm going to give you those rules, and as a matter of fact, they're on page here, already listed. But there is a real simple way to deal with significant figures called counting zeros, left and right, that makes this whole thing come together. But anyway, it's important that you learn the rules. One, all non-zero digits are sig figs. All non-zero digits are significant figures. If I have 1, 2, 3, 4, that has 4 significant figures. Now, in a general context, that last number in there will be a floater, as I call it. Okay, 1, 2, 3, 5, and somebody else comes up 1, 2, 3, 6. I come up with 1, 2, 3, 4. Okay, so it's the number of known digits plus one uncertain digit. Okay, so always the last one in the list is the uncertain digits that's listed. Okay, so now we'd come to the second rule, enclosed zeros. And now significant figures revolve around defining the zeros of a measurement, not just the non-zero digits. Enclosed zeros are sig figs. 101, that is an enclosed zero. Here. So this would be significant in your measurement, and this would have 3 sig figs in it, so to speak. Now I'm not going to dwell on this because I want you to learn really the system that I'm going to be sharing with you in a minute. Trailing zeros in numbers that have a decimal are significant. trailing zeros and numbers with a decimal are significant because the decimal position defines the accuracy of the device you're using. You might make underline of that. Decimal defines accuracy of device, measuring device. Thank you. Sorry about that. Mine doesn't go out up here. I miss it back there. I'll try to get the IT to come in. I'm lucky. Fix that. But raise your hand if it happens. Thank you. It defines the accuracy of the device. You're on a top loader balance, for example. It might read out 123.22, okay, or 0.00. Well, those last two zeros have to be significant because they are defining the accuracy of that device. Now, the last digit, again, is the uncertain digit. It might float a little bit because whoever comes behind you measures the same thing, may get a 123.04 or something like that. But at any rate, the trailing zeros in numbers with a decimal are significant because they define the accuracy of the device you're being used. Leading zeros, regardless of decimal nature, are not significant figures. I'll explain. .0.00234. These are not sig figs. Although you got to have them for the dimension that you're working with. That's fine. But they're not classified as significant figures by the definitions that are in the books. These are non-zero digits, so these would be sig figs. So that answer would have 3 significant figures in it. Simple as that. Nothing. Trailing zeros. Trailing zeros without a decimal establish magnitude. That's all they do. And are not significant figures in a measurement. Decimal present or not present, doesn't matter. Trailing zeros that define magnitude are not sig figs. Distance to the sun on the average is 93 million miles. 93 million miles. The zeros establish the magnitude of the dimension you are working with. But they are not significant figures because those could fill up with a lot of variations due to orbital mechanics. But we, on the average, accept that as a dimension defining the distance from the Earth to the Sun, so to speak. These are your sig figs. These are trailing zeros that establish magnitude are not sig figs. Now, now to simplify all of this, let's see if I can. If the numbers are leading zeros in a number, they're not significant figures. For example, I'll go 0.00123. Okay, we already have the rule, leading zeros don't count. But count, if you see a number like this with 0 point whatever, count from the left until you hit a real digit. 1, 2, 3. Here is the first significant figure. And everything beyond that is significant figures. So if you have a decimal something or another, you count to the, you disregard the leading zeros and you just count them. All of them will work like this in terms of identifying significant figures. If the number has the decimal on the right side, okay, 83.2097 or something like that, you count from the left side until you find a significant figure. Well, the first number is going to be significant any way you look at it. So all 1, 2, 3, 4, 5, 6 sig figs. So numbers that have greater than 0.99999 will be counted to the left to right, and those which have zeros or fractions count from the left, and till you hit a number, and then everything else is a significant figure. It's a little shortcut. Now you need to know how to deal with significant figures in multiplication, division, addition, and subtraction. Let's start here with this one. In an experiment, you apply some formula, whatever it might be, and it involves a combination of multiplication, division processes, and you come out with an answer. You have calculator answer that is, a bunch of digits long, but not all those digits are significant digits. How do you tell from a calculation how to round your number to significant figures, to identify significant figures? The measurement number having the least number of sig figs in computation defines sig figs in answer. So you just look at, say, x is equal to 203 times 14 divided by 611 and 4. And so you punch it into your calculator and you get an answer. Get my calculator to working. So we punch this in, 203 times 14 equals divided by 611 equals divided by 4 equals. Okay, so we get a calculator answer. 1.162847791, what the calculator answer shows. How do you express your answer? Well, there's only one significant figure in that digit, that measurement number. So that would define how you round that number to your answer. Probably like that, okay? Or just one significant figure, be fine. Now, if this happened to be, say, 6 right here, we use the roundup method and go to the next higher number. But the number in the computation with the least number of significant figures defines the number of significant figures in the answer if you're multiplying and dividing. Now, if that's confusing to you, I suggest you kind of grab the book and read up on significant figures. I don't beat you to death on significant figures because they are straightforward. Okay, and I think you, with a little common sense, you know this is not going to be the number to be reported. Also, significant figures, and I didn't mention this, really reflect the accuracy and precision that's within the experiment too. If this defines your experiment, some outcome that is one digit, okay, regardless of how accurate the other digits are, that's going to control the outcome of the experiment in terms of the overall accuracy of it. Okay, we'll work with that when we do the density of, not density, with the R value, the universal gas constant. We have an experiment we're going to run. And the device with the greatest degree of accuracy is 0.1. Okay, even though you're going to use a balance that's 4 digits past the decimal. You don't use that 4 digit past the decimal measurement in your final answer. You round it to the 0.1 accuracy of the measurement. Okay, that's multiplication division, and we've got enough time to do addition and subtraction, and next time we'll begin with systems of units next time. Okay, addition and subtraction, significant figures. If you have a series that you have to add together or some numbers you have to subtract from one another, how do you define where to round the number of your answer? Well, let's see, 101.111, and then we're going to have 2.3 and 41.75. Okay, there. And that's good enough, and you'll understand it when I go through this. When you add this together, you've got positions here. That's the 1, 5, 6, 7, 8, 9, 10, 11, 2, 3, 4, 5. Okay, 4, 5. Okay, so this is your calculator answer right there. Well, according to the rules, you round this to the least number of digits to the right of the decimal. To the least number of digits to the right of the decimal would be here. You see, there's not actually no digits right there. So if you have one digit to the right of the decimal in your collection of numbers, your answer is rounded off to that position and the measurements. So in conclusion, if you would, 5.2 would be the appropriate answer for that summation. Same way with subtraction. If you have a number here and you subtract that number from that number, it's still rounded to one position to the right of the decimal. Okay. Okay. Looks like, just for your information, okay, we'll get into systems of units. Dimensional analysis. Hopefully we can get through that in one lecture and complete the work. Okay.